Okay, so welcome to our sixth lecture on logic and dealing with propositions, propositional functions, which are these like things involving predicates and variables, right? And then once we learned about propositional functions, we learned about quantifiers. How do we quantify a propositional function in terms of its domain, right? Anytime you encounter any function, you need to be interested in what the domain is. So in today's lecture, we're going to extend this notion of quantifiers to multiple quantifiers. In particular, we're going to nest them back to back, right? And this notion makes for richer statements where you have more than one variable, right? So like maybe like last time, our last logic lecture, we were looking at things like for all x squared is greater than or equal to 0, right? That's like an example of a universal quantifier. And then so this reads for all x squared is greater than or equal to 0, right? So, but what if we have more variables, right? And I think the easiest way to illustrate this notion is just by giving an example. So, like today, we'll consider things that look like maybe this. For all x, for all y, x plus y is equal to y plus x. Okay, so notice how I was reading this out loud. So it's important to know how to translate these logical statements into words, right? There's a lot hiding behind these symbols. And you got to think of it like a human would, right? So how would this read? So this would be like for all, well, wait a minute. There's something I warned everyone about last time that we talked about these things. We need to be very careful about the domain. Like what's the domain of interest, right? So currently it doesn't say anything. Let's just assume, unless I say otherwise, that the domain of interest for these variables is just a set of real numbers. Okay? So if that's the case, then this would read for all real numbers x, and then and for all, I use the assembly, and for all real numbers y, x plus y is equal to y plus x. Okay. So that's how we would read this. So is this true for real numbers? Yes. This has a name, right? Yes, there you go. So there's the commutative property, associative property, and distributive property. That would be commutative, right? Now, okay, so, but again, like this is one way of saying it. Another way, it's kind of important, I think, to think about other ways of saying it, to communicate what this is like trying to express better. Like becoming, like in general, being able to communicate technical concepts to someone that doesn't understand it is going to be important for all of us, right? Imagine you're at a job, right? Most people will not have a technical degree like you do. So you have to somehow translate what you're doing and think of as many different ways that you can to describe that to someone. Okay? So what's going on here? Maybe we can say for any real numbers x and y, the order of the sum doesn't matter between x and y, or something like that, right? There's so many different ways to think about it, but I encourage you to try to think of different ways to write it out. Okay. So maybe let's try another one. Now we're going to start just doing a bunch of examples until we understand the idea of it. So I'm going to write it out first and then say what it is. Okay, bunch of symbols, quantifiers, parentheses. What's going on there? What does that say? Again, the domain of interest is real numbers. Perfect. Perfect. Yeah. So that's exactly it. So for all real x, I'm running out of room. I wouldn't write real numbers, but y'all get what I'm saying. For all real x, there exists a real y such that x plus y is equal to 0. So is this true for real numbers? How would we even determine the truth value of it though, right? Like this one was kind of easy to think about, right? But now this one, whenever they switch up or whenever the existential quantifier pops up, it's almost like you have to pause, right? When you're saying it out loud. So for all x, fine. And then this is like, we have to stop, there exists something. Right, so it's like, it's almost implying that this second one is dependent on the first quantifier, right? It's like these are tied together now in a weird way. A very specific way, right? So what's another way of like saying this statement?
There is some x for every y.
I think it's almost hard to think of a different way of saying it, right?
Mm-hmm.
Because that seems like this is like reading it out loud, but maybe we can just take some guesses, and I'm just kind of throwing them out there like for any real number x, there's something that you can add to it that makes it 0.
For every x, we can add a negative number to basically set number negative.
You're kind of I like what you're saying. So this is, by the way, the additive inverse property of the real numbers. Every real number has an additive inverse. That's like a technical way of saying it, right? So I would like to really focus on this one for a moment and break it down into its pieces so that we fully understand how to work with these types of nested quantifiers. So hopefully you remember from the previous lecture on quantifiers that we can represent universal and existential quantifiers as conjunctions and disjunctions respectively. So like, let's just recall that notion. So recall that for all x, p of x, this is the same thing as saying like p of x1 and p of x2 and p of x3 and ... That's a conjunction of the propositional function evaluated over every element in the domain. Okay, with the caveat again that technically speaking, we can only write out this list if the domain is what's called countable, but we can ignore that for now. This is the general idea. So then, and the existential is, well, it's the disjunction in this manner. So p of x1 or p of x2 or double check something, okay. P of x3 or ... So if you recall these notions, then we can take this guy and break it up. Okay, and what do I mean by that? So let's just start with it. For all x, this y, such that x plus y is equal to 0. Okay, starting here, just distinguish it from our little piece right there. All right, so what we can do is just treat this as like a propositional function, right? I can, for any y, the variable x is like the variable input to, the for all x, right? You can treat that like its own propositional function. And just think of this as the universal applied to this thing in blue. So it's going to look messy, but I hope that the idea remains the same. So what is this? Well, it's like this thing. So there exists y such that x1 plus y is equal to 0. And I need to reword what I said a moment ago, and I'll explain why in a second. And then there exists y such that, I'm running it through, I'm getting squished. Okay, and there exists y such that x2 plus y is equal to 0. And I'll just write out one more. There exists y such that x3 plus y is equal to 0. And dot, dot, dot. Off forever over all possible x in the domain of interest. So then that's just a number, right? That's just a single number. So does there exist a number that makes this true? A y that makes this statement true? Yeah. Negative that number, right? So that's going to be true, right? So, and this is just like what we were doing last time. Like that's a number, we're fine. So it's going to be true. And what about that one? Well, that's just a number again. So that's going to be true again. And true, all the way through. Which means that this conjunction is going to be true. Okay. So that helps us understand it. Now, whenever I'm looking at these logical statements, I always pause and think about the negation of it, of the statement in question. Like, what is the negation of this thing here? This is true, so the negation got to be false. What is that statement? Right? So we just have to recall another fact from a previous lecture, in lecture 5, and that's De Morgan's laws, right? Applied to these quantifiers. And there's two of them. And there's the negation of the universal is logically equivalent to the existential of the negation. And the negation of the existential is logically equivalent to the universal of the negation. Okay, that's from last time. Now, let's see if we can figure out what the negation of this statement is. Okay, so the negation of, for all x, there exists y such that x plus y is equal to 0. So again, we can treat this like a propositional function, right? So not universal becomes existential of not whatever this is. So this will be logically equivalent to the existential, like that, of the negation of this other stuff. And again, like this is like the propositional function right here. Treat it like the P. So not universal becomes existential of not whatever that is. But then we apply it again. We have not existential and then a propositional function. So then this will become, so that stays the same, and now that's going to become the universal. And then we pass the negation in. Really close now. So we have to negate that propositional function. So what's the negation of x plus y is equal to 0? Right, x plus y is not 0. Right? So the final line would be, there exists x for all y such that x plus y is not equal to 0. So that's the negation of that statement there. Now, if we did it correctly, this better be false. So let's say it out loud. Okay. So they're just a real number such that for all real numbers y, x plus y is not equal to 0. False. That's false, right? Over this a little bit. Right? So this is false because, well, if it's false, then we should be able to provide a counterexample. Remember, a counterexample to a universal quantifier in this instance is just a case where it fails, right? So there exists x. Pick any x you want, like 0. We can pick like 0, yeah. So if x is equal to 0, so that's set in stone, right? For every possible real number y, x plus y is not equal to 0. What y would make it actually equal to 0? Exactly. So this right there would be a counterexample of that, making it false. Which is good. It better be false because the original one we kind of argued was true. Okay. So, somewhat clear on how to work with these things? Okay. Now, how many of you in here have taken or are taking Calculus 1? Okay. I'm assuming that everyone in here must take Calculus 1 at some point. And there is a definition that you encounter early on in Calculus 1 that I'm like 80% sure that the majority of you didn't understand. Right? The first time you take calculus, when you enter Calculus 1, you're still in like the mindset of like computing things and like just getting the answer. That very few students actually take the time to understand what the definitions mean. Okay? So I'm going to write out the most fundamental definition from Cal 1 and see if you recognize it. Okay, so here it goes. This is a definition from Calculus 1. If you haven't taken Calculus 1 yet, it's fine. This might help you when you get to the class. So I'm just going to write it out without saying much about it at first. There's the most fundamental definition that you encounter at the beginning of calculus 1. Something is equivalent to this. So this is like logically equivalent to some statement. Any guesses? Well, maybe we should read it out loud. For every epsilon greater than 0, there exists a delta greater than 0, such that if, so that's the conditional right there, right? If x minus c is less than delta, then f of x minus L is less than epsilon.
Does it have fundamental theorem in calculus?
It's not a theorem, it's
I've
a,
never seen that before.
oh no, you most definitely have.
It's
If you-
derivative, right?
Nope, it's more fundamental than that. So let's deconstruct this definition some more. Okay? In like words like that we can understand. Okay? So for every epsilon, okay, so epsilon is just some positive number. Okay. There is a delta, there is following the for all. So it's almost like the delta is tied to the epsilon in a sense. Okay. Now what is going on here? When you see the absolute value of a difference between things, what do you think? That's a distance. So the distance, one way of measuring distance between two numbers, A and B, is with the absolute value of the difference. Okay? So think about it, like what's the distance between 6 and 4, right? Or 4 and 6, let's do 4 and 6, so you can see why. So put a 4 there, put a 6 there, 4 minus 6 is minus 2, and absolute value is 2. They're 2 units apart. So whenever you see that, you should immediately start thinking distance. So let's now kind of reword this. So this is the distance between X and C is, I'll say at most delta. At most means it's less than, right? That's right there. Distance again. So this is the distance from f of x to whatever L is at most L. So x is a variable in this case, right? This thing can vary no matter what. Like this is any positive number, right? So this is any positive number right there. But for each of those, no matter which one you pick, there is some delta with it. It's like paired up with it, right? So that anytime x, well, no, I'll just say it out loud. The distance from x to c is at most delta. Implies that. So the distance from x to c is at most delta implies the distance from f at x to L is at most O. Why didn't y'all catch me? It's an epsilon. Most epsilon. So still no clue? It's okay. It's fine. I'm gonna help you. We're gonna find our way there. Okay, so I need a lot of boardroom for this. Maybe, yeah, I might have enough for right. So functions, right? Functions, this seems to be like a real value function for whatever reason. I'm just assuming that. So what do functions do? You put in a real value, you put in a number, and you get out another number, right? So just for the sake of understanding this in a very abstract way, imagine that's all real numbers in that block. Okay? And then the function f is that. Right? It takes a real number and it spits out another real number. So just abstract it with me. All real numbers in here, all real numbers in there. Right? Yeah, exactly. Now, it's not going to output all the real numbers, maybe. Maybe it'll just be like a subset over here. Maybe it'll be a subset over here that it goes to, right, depending on its domain and range, but that goes from there to there. Now, in order to understand this definition, let's suppose this is true. Like suppose that that's a tautology, right? And just see if we can gain any information about what it's trying to say. Well, if it's true, that means I can pick any positive number I want to start off in understanding it, right? So I'll say like, for every epsilon, I'm just gonna say pick epsilon not or something. Some number, right? Like, I don't know, maybe like 1, whatever. Okay. Now, as soon as I do that, since this is a tautology, we're supposing it is, I get a delta immediately. I must have a delta. So then I get a delta. So get some delta. I'll call it delta 9. I don't know how big it is or whatever. I have no idea. I just know it's greater than 0 and it's associated with epsilon equal to 1. So following? All right, so we're just working our way down the line. Okay, now, conditional statement. We only need to worry about the conditional statement being false when the hypothesis is satisfied. False hypothesis, the whole statement's true, whatever. It's called vacuously true, right? But what we need to do is check what happens if that's true there, right? And since we're assuming that this is a tautology, if that's true, then that better be true too. Okay, so to kind of visualize distance in these blobs, well, before I get there, there's some C that's related by distance with some X, possibly, right? So maybe I'll put like C right here. C. And then there's an L somewhere maybe related by distance with the output of the function. Maybe I should make this block bigger. Yeah, so maybe like L is like right there. Right? So for the purpose of visualization, to illustrate distance from X to C at most delta, I'm going to do this. I'm going to start at delta, and I'm going to extend out. I'm going to start at C and extend out the line of length delta. Okay? And then I'm just going to turn it around. So anything that lies in that ball right there will be within distance delta to C, right? So suppose like I take like that point right there. I don't know, just call it like X. That's a point. And notice, just hopefully everyone can see that there is a ball around C, and anything in that ball is within distance delta to C. So since X is in that ball, it must be within distance delta to C. So that X satisfies that. Okay, which means it better satisfy this. So there's some like, I'm going to do the same thing with epsilon. Maybe it'll be like a little bit smaller. There's epsilon, length epsilon there. I'm just going to make a little ball around L. So anything in that ball is within distance epsilon to L, right? Oh, now we know something about where that blue X gets sent. It better be in there, right? The blue X better land like right somewhere in here. That's F at X. It better be in there. Like if this is going to be a tautology, if I pick anything in there, it better be in there, right? So that's like one instance of epsilon. This has to hold for any instance of epsilon, right? So that's a big epsilon. What about if we say, without the not there, looks like epsilon equal to like 1 over 2 to the power like 10,000. Some incredibly small number. That's tiny. It's basically nothing, right? But again, if that's true, right, if this is a tautology, we get some delta. Right? Because this has to be true for any epsilon we pick, even that tiny one. So then, coming back over to my picture, and now I'm going to do it in like the appropriate order. Earlier I started there and then looked back and came back. This is how you really should think about it now. You have that, so there's some relation with the distance between f of x and L, right? So in this case, when epsilon is that small, here's your ball. It's like on it, basically, right? That radius is so small, it's like just on the point. But no matter, because we're assuming this to be a tautology, that means that there is some, I'll draw it in blue this time maybe. There's some distance around C with delta, right? So then no matter what I pick in there, right? No matter what I pick in there, it better land over there. All of those points. Every single one, right? And there's like an infinite, uncountable number of numbers in there. All of that, it's like, you can think of it like this, honestly. It's like everything, all of those points get shrunk down to be in that little red dot. If we're assuming this to be a tautology. Which means what? Well, it means that no matter how small the distance around L we pick, there's an infinite number of points around C that have to get sent inside that tiny ball, no matter how small. And notice that just looking at it, you can't even see the ball right here, right? Intuitively, or like maybe with words, we can describe this as pretty much those infinite points, F at any point in there, it's L, right? It's basically L, which means that this definition is really representing this notion. This is the definition of the limit as x approaches c of f of x equals to L. That's what that definition is. If this is always true, a tautology for any choice of epsilon, that's what mathematicians came up to describe this idea, right? Again, this is logically equivalent to this statement, right? If this is true, then that's true. If that's always true, then that's true. They're equivalent, right? So I hope this makes you think back to when you're taking calculus courses or any math courses, you might see statements like, for every this, if this, then this. So this is the using symbols, but in a textbook, this would probably be, for every epsilon greater than 0, there is a delta greater than 0, such that if x minus c is less than delta in absolute value, then the absolute value of f of x minus L is less than delta. It seems convoluted, but there's an idea there, right? And this is an important fact of like all your mathematics courses going forward, that yes, you have to worry about computing things sometimes, but really to like really nail it down, trying to find what's hidden, what the idea means, will help you like understand what's going on when you're computing, right? So like, for example, just thinking about it, like if there's some point over here that gets mapped right there, oh, that can't be the limit. Even if it's only one, right? Everything in there has to be compressed into there. That's the idea. It doesn't have to equal it, it just has to be compressed and basically equal. So it looks different than what your textbook would describe the limit as with a picture. But just to like really make sure that we understand what's going on here, in R2, so how can we translate that picture to this one now? Well, you just take everything here and you squish it onto an ordered line. Right, so like this right here would be like this line here, this x-axis. All of these right here, they're this axis. Okay? And we visualize the pairs between them by putting points over here. But x-axis, y-axis, that's all it is. So let's assume that it's true for some function. Like, so here's like C, C's in this one, right? And then maybe like L is right here. Okay. Let's make a little ball of radius delta, or epsilon first. Let's start with epsilon. So it's like, go up epsilon, and where are you at? L plus epsilon. And then circle around. Oh, here's the other part on that real number line. So we can ignore the balls now and just think about only like right there. L minus epsilon. Okay. And this is any choice of epsilon we want. What do we get? We immediately must have a delta. So make a little arm out of length delta. Where do we land? C plus delta. Okay. Wrap around. The other side would be C minus delta. And now we know what happens. We know what happens, right? Hopefully we do. Like, pick any number in here. The function's value has to be where? Somewhere in here, right? So like, I pick that number, it better be like there. all the possible points that you would plot have to be within this range of L on that interval, on this interval only. That's the only one we're guaranteed, so it's like, it has to be like somewhere in that interval, okay? All those values are stuck in. Every single one in this interval must be in there. If any one pops out, this would be false in that case. That would be a counterexample to this being true, so it's false. Yeah. So hopefully this illustrates how you can use these quantifiers and propositional logic to help yourself understand technical mathematical definitions, but also just breaking down statements into their components to help you understand in general. Okay. So honestly, I think that'll be it for today's lecture. I'm going to go ahead and stop it there. We've illustrated these points, and then in the description of the video when I post this to YouTube, I will put a link to my previous lecture on this topic so you can see other types of examples as well. I didn't do this one in that lecture, so it'll be nice to just add them all up. Okay.